Okay, so this problem reads, a 7-kilogram person is riding in a car moving at 20 meters per second when the car runs into a bridge abutment. Calculate the average force on the person if he's stopped by a padded dashboard that compresses an average of 1 centimeter. And then we're going to look at that same scenario when the airbag is used and the average force when it compresses by 15 centimeters. So sort of looking at how that airbag and dashboard help you. The airbag, of course, being the more important one. All right, so if we want to determine average force, we need to look at the acceleration on the object. Remember, force is equal to mass times acceleration. And so we can assess what is the acceleration of this object as it runs through into that abutment, and then goes through that compression of the dashboard or of the airbag. And so we're going to look at the acceleration in a kinematics way, which wants to remind us that we have to understand what's the initial and what's the final. So the initial is when the driver hits the dash. And the final is when they come to the stop. So if we're looking at our picture, we're really looking at the driver itself kind of hitting the dashboard. There's my driver running into that dashboard. And we're going to call this our position equals 0, right at the point they hit the dashboard. Okay, so we're going to make our list of variables so that we can determine the acceleration and then get that average force. So the person starts out at the dashboard at 0, compresses by 1 centimeter, so 0.01201 meters, 100, I know that's too many, that's a millimeter. I was right the first time. 0.01 meters. That's meters. It goes 0.01 meters. We're told that they're moving at 20 meters per second. And they come to a stop, so 0 meters per second. We don't know the acceleration and we don't know the time. So what are we interested in? We're interested in this acceleration so that we can solve for the force. So we're going to use the equation that gives us acceleration, but we don't need time for. That was our v final squared is equal to v initial squared plus 2a delta x. So v final is 0. V initial is 20 squared plus 2. The acceleration is what I'm interested in. And my change in x is 0.01. Minus 0, but we have 0.01. So when I solve for this, I get an acceleration of negative 20,000 meters per second. What does that negative tell me? Well, it tells me the acceleration is opposite my direction of motion, which we know must be the case because we're slowing down. So when we're slowing down, if our acceleration and our direction of motion are opposite, we slow down. So I can then use this acceleration in my average force equation. I have a mass of 75 times my acceleration of 20,000, and I'm just going to determine the magnitude of that force. We find that force is equal to 1.5 times 10 to the 6th newtons. So pretty big force. What's the airbag do for us? So we actually have the same initial and final conditions, but in this case, we're hitting that airbag. So we're coming to a stop over a different distance. So the only thing that is going to change in our problem is our initial conditions. And our known values. So our initial condition is actually the same, but our final is now 0.15 meters instead of that 0.01 meters. V initial is still 20 meters per second. V final is still 0 meters per second. I don't know the acceleration, and I, of course, don't know my time. So once again, I'm interested in this acceleration. I don't have time, so I'm going to use that same relationship I did before. And so we'll use this relationship, and we have 0 is equal to 20 squared plus 2 times the acceleration. And in this case, my delta x is 0.15. So if I solve for my acceleration, I find that that acceleration in part B is negative 1,333 meters per second squared. Again, that negative tells us that our object is accelerating in the opposite direction of the motion to the left, and our motion was to the right, so it's going to slow down. I can then use that acceleration in my force equation. I'm just going to look at the magnitude. We have 75 times 1,333, and we find in this case the average force is 1 times 10 to the 5th newtons. So less by an order of magnitude in terms of whether I hit that dashboard or I hit that airbag. So thinking of average force, knowing we need that acceleration, and then using our kinematics to find that acceleration. All right, good job.